So in 4.9, what we're going to do is we're going to study inequalities again. We're going to take a look at inequalities. And we're going to take a look at them like they're equations at first, just like we did with linear inequalities. You solve them like it's an equation, but then you apply the greater than or the less than symbol, whatever it may be. We're doing that again today. We're going to solve these like they're equations. They're going to be quadratics. We're going to have to factor. That's why I said factoring isn't going away. You're going to use it in the next few chapters. It's going to keep coming up. So we're going to factor, and then what we're going to do is we're going to identify remember the roots of the equation? When we found the factors and set them each equal to 0, we're going to do that again here. We're going to call those, in this unit, critical points. I think we used the term critical points once before. When we were doing absolute value inequalities, we talked about what that starting point was and the deviation when we solved graphically. That starting point is like the critical point here, same idea. But the zeros are just going to be named critical points. The reason I'm using that term, critical points, is because when you get to calc, you're going to use the term critical points in this application. Okay? So I'm continuing to try and go along with vocabulary that you will see later on, so when you get to those classes, you're familiar with it. And your teacher doesn't have to go over what the terminology means, or you can understand it much quicker. Okay, so again, we're going to solve these like equations, and then we're going to go ahead and take a look and identify what's going on. So that's kind of what I just said here in this section. Okay, so if you're looking at the notes on yours, you can read through that. But again, we're going to look for these critical points. Okay, then we're going to create regions on a number line. So all the critical points we're going to mark on a number line. So let's say we had 3 critical points. We put a number line out, put the hash mark at those 3 critical points, making 4 different regions on the number line. Okay, regions, like when we had 2 overlapping sets on a number line, we look for the region of overlapping. So we're going to create regions where those critical points exist. And then we're going to test each region by evaluating one of the members of the inequality. That means we're going to test a point in the original. We're going to mark the region as positive or negative, and then shade again. Remember with linear inequalities when we graphed? We would test the origin, and if it worked, we shaded that side of the graph, and then we do another line and shade it, and we look for that overlapping of shading. Same idea here with shading, but on a number line. Okay, a little more basic, not on a graph. Let's take a look at this to see what I'm talking about now. So for a problem like this, again, imagine it's equals and not an inequality symbol. So start by writing it that way if it helps you, please. You don't have to write it this way. You can continue to write it the way it's shown. But if you want to start by writing it this way, please go ahead. Now, another thing I should mention, and this is a remark for your test, some people forgot the first step of factoring. No matter what you do, the first step is always the same. What is the first step of factoring? The GCF. You can't factor sometimes unless you find the GCF. It doesn't always work. Liam, what do we have here? Yeah, so it becomes y times the quantity.
Y times the quantity, y minus 3.
Good. And for those that had trouble factoring out a GCF, because some people made mistakes here, you just have to divide by whatever you factor out. Do that in your mind. These y's cancel, giving you 3 or negative 3. This y cancels with that squared, giving you a y. So this is our equation. Y parentheses y minus 3 equals 0. How would I solve this if it were an equation? Forget that's an inequality, Georgia. Equation. Very good. So we set each factor equal to 0. Whenever you factor out a variable, we have to set that variable equal to 0. Now, these are my 2 roots of the function, or roots of the equation, or zeros of the function. It's not a function, so we wouldn't say zeros. We would say roots, though. The roots of the equation. We can identify these as what are called, again, critical points. So let's write that down on the side. Just put either CP or critical points. These are the critical points. Remember when we graphed? When we graphed these, what were they on the graph? What were they on the graph? The roots of the equation were the blank of the graph. Fill in that blank. Were the blank of the graph. The blank of the graph. Ma'am? What's that? Not regions. Yeah, it kind of separates into regions, but they're not called regions. Yeah, which ones? The y or the x? The x, yeah. Remember that when we set the function equal to 0, it's like we're setting y equal to 0. This happens to be the variable y. That's why it seemed that way. This is just the variable y. It's a random variable. But the roots happen to be the x-intercepts. This situation is pretty much analogous. See this number line I've drawn here? Doesn't it look like an x-axis? So it's like we're doing the x-intercepts again. Again, this looks like an x-axis. So we have critical points at 0 and 3. At 0 and 3. So what I'm going to do there is start by putting a dash here and put a dash here. At 0 and 3. Okay? Now, what I need to do next is to test each region. Pick a point in that region and test it in the original equation. The original equation at the very top of the screen here. Okay, so pick a point that is in this region. Tell me a number that's in this region. Doesn't matter what number, worth. -2. Another number, -3, -7. Anything left of 0, anything negative is in this region. What is the easiest number to test that is negative? -1. Because you don't have to worry about multiplying or squaring ever. And if you square a negative, it just becomes a positive. So any number can work, as Worth showed us, but we're going to say that we'll use simpler numbers. So over here, let's test -1, which means plug -1 into the original. Plug -1 into the original at the top. -1 squared is +1. -3 times -1, or -3 times -1 is +3. This becomes 4 less than or equal to 0. Okay, now right away, is that statement true? No. It's not. So this is not going to be one of our answers. But what I want you to do is this. Just look at the sign. 1 plus 3 is definitely positive, right? So mark this region off as positive, please. So look at this answer here. And because of this answer, mark that off as positive. In the second region, what number am I going to test? The other easy number. You can't test 0 because it is a critical point. You cannot test your critical points. Austin? 1. And 1 squared is 1. Minus 3 times 1. 1 minus 3, that's definitely going to be negative. I don't care what the number is. It doesn't really matter. All that matters is that it's going to be negative. Okay, we're going to have 1 minus 3 here on the right-hand side here at the bottom. That's going to be negative. And then finally, test the number bigger than 3. Pick 4. Use whole numbers. Use numbers that are the smallest as possible. So if I test 4, it becomes, I'll do it on the upper left here. It becomes 4 squared minus 3 times 4. 4 squared is 16 minus 12. 16 minus 12 is? 4. Yeah, and generally speaking, it is positive, right? So all I have to need is positive here. 16 minus 12 is most definitely positive. So I test all the regions, and I show my work. Please, people, don't just do this and not show work. Show your work here so you can see what's going on. So we've got positive, negative, positive. Everybody see that on the number line there? Now, Arthur, the original equation set the variables less than or equal to 0, right? What does less than or equal to 0 mean?
It needs to be 0 or negative.
Yeah, it needs to be 0 or negative. Well, the only region that is negative is the middle region. So we automatically shade that region. Because it was less than or equal to, we put colored in circles at the ends. Okay? And that's our solution set. We'll finish this off tomorrow. Okay, just in solution set form, it would be between 0 and 3. Okay, and it's y, not x. It's y, not x. This example was not recorded in class due to some technical difficulties we had, so quickly to explain it. We have an example of x squared minus 2x minus 8 greater than 0. We start by factoring it. So we can see here in the middle that it's in factored form, and thus identifying the critical points. Mark the critical points on a number line. Test each region. If here you test 0, you'll get 0 minus 4 and 0 plus 2, so it's going to be a negative times a positive, which gives you a negative. Here if you test a number like 5, you get 5 minus 4 and 5 plus 2. That'll give you a positive, positive, giving you a positive here. Here testing negative 3. Negative 3 minus 4 is negative 7. Negative 3 plus 2 is negative 1, giving you a negative negative multiplying to be a positive. So since our solution, or since our problem asks for when this quadratic was greater than 0, we want the positive regions, which are these regions right here. And therefore, the solution set looks like the following. X greater than 4, which is this region, or x less than negative 2, which is this region. Open circles, because we're just greater than or less than here. Example 3 says, find and graph the solution of quantity x minus 2 squared less than or equal to 0. Now this is a tricky one. What does the quantity x minus 2 squared mean? What does that really mean, Francis? Yeah, that's what it really means. So we have roots to the equation that happen to appear twice. What do we call that again? A double root or a multiple root. We could also see that there's a double root simply because this was squared. Whenever you have something squared, like a factor, something in parentheses squared like this, it's going to appear more than once. So we have x equals 2 as our critical point, and the other critical point is also x equals 2. So that means that there's really only one critical point in this problem. So here's what we do. We put our critical point here at positive 2. Did I say negative 2 a minute ago?
No, you said positive.
Okay, good. Okay, they're the same critical points. I'm going to write them twice so you can see that, but it's the exact same solution when you make your t-chart there. Now, since the critical point repeats itself, we've been talking about how this is indeed a tangent on the graph and stuff because it's a double root. But right now what's important is that we go ahead and test our regions. Okay, we test our regions. Now, this is less than or equal to. So right away, is this going to be an open or a closed circle? Why, Fiona? Yeah, this little equal to symbol under here means it could be that value also. So let's put a closed circle there. So let's start by putting a closed circle right here. And either we're going to shade to the right or to the left, or neither, or both, depending on what these regions give us. So tell me a number bigger than 2. Pick a number bigger than 2, Natalie. 3. Natalie, if I plug 3 in both of these cases, this 3 minus 2 gives us, and this is also, and 1 times 1 is still positive, isn't it? So this is a positive region. Austin, give me a number so you have the last one over here. Pick a number. 1. 1 minus 2 is negative. 1 minus 2 is negative. Negative times negative is a. So this is also a positive region. Interesting. And this is what I was saying before. Don't try and think that they're always going to alternate positive, negative, positive, or anything. Okay, Summer?
I was going to say,
Yeah?
so wouldn't it be no solution because
Very close. There's no shade. There's no region we're going to shade, and she's absolutely right.
it would be just 2.
Yeah, just 2 because there's a closed circle there. Very good. This problem wants us to find out when it's less than 0. Less than 0 means, everybody, what does less than 0 mean? But we have 2 regions that are both positive. So the solution is not in either of those regions. So because this was a closed circle, 2 is one of the solutions. But it's the only solution in this problem. And try it. Plug a 2 in up here. 2 minus 2 is?
0.
And 0 squared is? Is 0 less than or equal to 0? Yes, it is. It's equal to 0. It's not less than 0, but it happens to be equal to 0. So the only solution here is x equals 2. There is no region to shade in. What if this had been just less than 0? Not less than or equal to 0?
No solution.
No solution, because this would be an open circle, and we wouldn't have shaded anything in. So therefore, no solution. What if, this is where we have to start thinking outside the box now, what if this had been greater than or equal to 0? Greater than or equal to 0. All real numbers. Because when it says greater than or equal to 0, the question is saying, when is this positive? It's positive here, it's positive here, and this is colored in, so clearly this is part of the solution. So everything would have been shaded in, and thus all real numbers. Trickiest one of all. What if it had said just greater than 0? Not greater than or equal to 0, but simply greater than 0.
There would be So it'd be all real numbers except for 2.
Exactly. Very good statement. It would be all real numbers, because greater than 0, these are both greater than 0 regions, but this would be an open circle. So it'd be all real numbers except for 2. It would be like, remember those domain problems where I said, find the domain of the problem, and it was like all real numbers except for 3 and except for 5, because those made the denominator 0, making our fraction undefined. Same kind of idea here. It'd be all real numbers except for 2, had that been the case. Okay? So do you see how one problem like this can give you 4 completely different answers? So this symbol here is extremely important. The inequality symbol that you're seeing at the top here is very important to our solution. Okay? 3 was a tricky one. Let's take a look at 4 now. So start by factoring. Right away, what can I factor? Liam? Good. GCF. What's left behind, Liam?
The 30 squared minus 16.
And clearly we should all remember after that test that this is not completely factored, right? Okay, number 2 from the last test. Fiona? Very good. Difference of 2 squares. It's obvious because of the 16. Okay, it might not have been as obvious on your test because it was a 1 there, but that is a perfect square. Now we have 3 solutions here, don't we? So we'll have 3 critical points. Please, folks, remember, you cannot make this T-chart or this column chart until you have all factors. Wherever there's a multiplication symbol, you see this vertical line separating these columns. Multiplication symbol, vertical line. Dave?
Actually, how I solve it is I solve it from there, but since you square root it, it's plus or minus 16.
Exactly. Like when you do the square.
Yeah, plus or minus the square root of 16, which will give us...
4 and
Very good, Dave. You could do that also. And I think we did that in one of our examples in class. You could solve it either way. That's absolutely fine. So those are our 3 possible answers as results of our factors. Those are the roots if we had an equation. Those would be the roots if we had an equation. But here we have an inequality. So in this problem, these are not the roots, but the critical points. Let's make a number line. How many regions do I have to test now? 4. So it can get a little annoying at times, okay? But please, I'm going to recommend to you, it might be useful to use the factored form to test it in than the original, because you don't want to have to be cubing numbers bigger than 4 and doing a little bit of math there. Use the factored form, and here's what I mean. A number bigger than 4, how about 5, right? How about 5? Let's take 5 and plug it in here now instead. What's 5 plus 4?
9.
So this is positive, right? What's 5 minus 4? Which is positive. And then I just put a 5 in here for W, which is positive. What's a positive times a positive times a positive?
A positive.
So this is positive. Do you see how much easier it is to test it in the factored form? That's why I recommend that. Mr. Linus was the one who recommended me instruct you guys this way. And it really does work much better. Okay, because it's the way he teaches them in calculus to do it. From 0 to 4, pick the number 1 again, right? The number 1 is easiest. You could plug the number 1 in up here and clearly see that it's going to be negative, right? Because you get 1 minus 16. Or you can plug the number 1 in your factored form. You get a positive for the number 1. Then 1 minus 4 is negative. Then 1 plus 4 is positive. Positive, negative, positive is a negative answer when you multiply them. Okay? Then we choose negative 1 next. Okay, we'll pick negative 1. I'll use green maybe, yeah. Let's go to green. If I plug negative 1 in, it makes this negative, because I'm plugging negative 1 directly in there. Negative 1 minus 4 is negative 5, so this is also negative. Then negative 1 plus 4 is positive 3, so this is going to be positive. Negative times a negative times a positive. What is it?
Positive.
Positive. Again, negative negative is a positive, times another positive is still positive. And I need another color. Let me go to pink. All right.
I was going to say brown.
So a number to the left of negative 4.
Negative 5.
Negative 5. I'm gonna put these markings below. Okay? So if I plug negative 5 in, I get a negative here. Negative 5 minus 4 is still negative. It's going to be negative 9. Negative 5 plus 4 is still also negative. Negative times negative times negative is a negative. So there's my 4 regions, and they happen to alternate. This pattern does occur sometimes, but it doesn't always occur. Okay? If you really get a good grasp of this and do enough practice problems, and you can pick up on it, that's fine. But I'm not going to go over looking at just patterns because they don't always occur. And I don't want you to just memorize patterns. But some of you might be able to pick up on it when you do your homework, that there are certain trends. We are trying to figure out when this expression is bigger than or equal to 0. So we're trying to figure out when it's positive. I've got a positive here and a positive here. It gets a little tricky though. What do I have to put above my critical points? Open or closed circles?
Closed.
Why?
Because it's and.
Yeah.
Sorry, it's greater than equal to.
Yeah, greater than or equal to. The equal to tells us closed. So let's go ahead and put a closed circle here, a closed circle here, and a closed circle here. Now, the only regions we're shading are the positive regions because the original problem said when is this greater than 0 or greater than or equal to 0, which means positive. So I can definitely shade in over here. And then what about the other part? Is there going to be an arrow involved there?
How do you shade between the two closed circles?
Yeah, between the two closed circles. Very good, Austin. That's the positive region. And it ends at the closed circles. So this is a line segment from negative 4 to 0. From 4 to infinity, that's a ray. And you learn about these basic shapes, but you'll learn more about them next year in geometry for sure, if those aren't familiar. But again, between negative 4 and 0, that's a segment. And over here, it's a ray extending infinitely in the positive direction. So the question becomes, what's our solution to this? What is our solution? How would I write the solution for that line segment in this little region between negative 4 and 0?
You do x greater than negative 4, or y,
Greater than negative 4. Greater than or equal to negative 4. Less than or equal to 0.
Okay, so it would be and, like this you're saying? Okay, that works. Or, good.
Greater than or equal to 4.
Very good, that's one way of writing it. So it's in between that region, it's between negative 4 and 0 here, or it's outside of it. What's another way, though, to write that first expression here? There's an easy way to write this. God bless you, Liam. There's a much easier way to write this.
0 is greater than or equal to w, which is greater than or equal to negative 4.
Less than or equal to.
Oh, that's nice. That's opposite. It's opposite. It's opposite.
Oh, you're writing it that way. Okay. So let's write it from left to right, though, just to be consistent, right? So tell me what would go over here then, really.
So that would be negative 4.
Yeah. Just write it in the way you see it. See how negative 4 appears over here and 0 appears on the right? Drag that down and copy it that way, okay? Good. So that's another way to write this expression right here. Okay, that can be written as we wrote there, or this last part still exists. Okay, so either one of these is fine. Personally, I would choose the second one simply because I see between negative 4 and 0 as a solution, so I can see that this negative 4 corresponds to this 0 corresponds to this, and the solution is in between them, so this W is in between them. Do you see what I'm saying? How it's analogous? This diagram looks like the solution as well. Or is like this big gap here, right? Remember these gaps have always been ors? So this big gap means or it could be to the right of 4, so or it could be greater than or equal to 4. All right, this is a tricky one for sure, because you're combining and or statements at once. Questions? Liam?
Actually,
No, please ask.
no, it's a stupid.
No, it's not. Please ask.
So if it was less than or equal to 0, we would shade the minuses.
Correct. So we would have an and statement again here. It would be 0 less than or equal to W less than or equal to 4, or W is less than or equal to negative 4. So it would be literally the opposite of what we shaded here. It would be shaded if that sign were switched. Not a dumb question at all. Very good question, okay? Again, remember when the sign switches to shade the other regions. I guarantee you that'll be a question on your test. Maybe not word or verbatim, but I might give you a solution set on a number line and say, Now the inequality has changed or flipped signs. What would the solution set look like then? You literally would draw the same number line, but just shade the alternating regions as opposed to the ones that you had shaded originally. Okay?
Oh, I was just gonna actually move back.
All right, let's take a look at the last one here. I think it's the last. Yeah, it should be. Okay. Looks like it's confusing at first because there's a lot going on. So it seems like it, but it's not that bad. It's really not that bad. What might be a way to go ahead and solve this one? Dave. You divided by h squared. Now, there's a simple problem with that. That works, Dave, but there's something that you want to be concerned about before you do that. That gets rid of two of the possible solutions. Remember how if you pull out an h squared as a GCF, you get like a double root from the h squared? When you divide by it, it kind of gets rid of it in the equation. So Dave's statement makes sense because he sees that h squared is on both sides. So he's like, let me divide by h squared. But that gets rid of that GCF that'll be pulled out front, which will get rid of 0 as one of our critical points. So this is one of the few times that you don't want to cancel things that are on both sides if they're variables. Had, say, for example, the number 2 been here on the left side, and there's a 2 and a 6, you could reduce them for sure. Okay, divide by 2 on both sides. But when there's a variable that cancels on both sides, you actually can't cancel it. And let me show you exactly what I mean now, okay? Let's distribute on the left side first. Let's distribute this to both terms here. This will give us h to the 4th plus 9h squared greater than 6h cubed. Now I'm going to move the 6h cubed over by subtracting it. And I'm going to put it in order. Do you see what I'm saying now? What would come out of all these terms? What GCF comes out of all three of these, Austin? H squared. And had we divided by h squared to start, we would not have that h squared anymore. But it's important because that is going to give us one of our critical points. Leaving behind h squared minus 6h plus 9. I'll leave it like that for now. What do I get when I factor? What do I get when I factor here?
H minus 3, and then H minus 3.
Yeah, they're both h minus 3. So we have a double root twice in this problem. We have two double roots. The h squared gives us a double root, and this quantity, h minus 3 squared, also gives us another double root. So if I want to, I could write this as follows. Just to indicate that they're both double roots. It doesn't really matter, because when I make my t-chart, I'm going to do this. Okay, those are my two critical points either way. The double root, triple root significance does not affect these kinds of problems. Okay, it doesn't really have any effect on our answer here. So you don't have to worry about that. Okay, but you should know that when it is something squared, these are both double roots. Now, for the sake of this problem, we'll just call them critical points. Now, let's go back and just quickly again look at the fact that this h squared did give us a critical point at 0. Dave, if we had canceled the h squared, we'd only have h equals 3. Okay? And that would be partially right at first. You would think it was right, but then if you tested another point in another region, it wouldn't work out. Okay? So this is one of those few times that you're not going to cancel things on both sides. It's only because it's a variable. So let's use 0 and 3 as our hash marks. Open or close circles? Open, because it's just greater than. Open circles. Now, it's greater than 0, so I want to shade in the positive regions. So let's test to see which region will yield a positive answer. What number is the easiest number to test on the left of 0, or to the left of 0? -1. I'm going to test it in the factored form right here. What's -1 squared when I square it for the h? +1. What's -1 minus 3? -4. -1 minus 3. So a negative now gives you a, and then that times a positive is still positive. So this turns out to be a positive region. So already we're going to shade over here. Okay, and we know that because of this symbol here. We want to know when this expression is bigger than 0 or positive. So it is there. What about the number 1? Let's test the number 1 now in that middle region. If I test the number 1, what's 1 squared?
1.
It's positive 1. What's 1 minus 3? What's 1 minus 3? So we have a double negative making it a positive, times another positive, it's still, yeah. So this is interesting. It's still positive. So we're going to shade here. But make sure you don't shade over your open circles, please. Okay, because those are not part of the answer. Open circles are never part of the solution. And then finally, let's pick the number 4. 4 squared is? Yeah, so it's positive. 4 minus 3 is 1. That's also positive and positive. So this is positive. So in the end, what do we have here? What do we have here? Except for which ones, Liam? Except for my open circles. What numbers are those? Yeah, very good. So x is in the set of all real numbers, except that x can't equal 0 and x can't equal 3. Okay, it's all real numbers, but it can't equal 0 and it can't equal 3. Simply because of the open circles there. That's why it can't equal 0 and 3. Before we do anything else or talk anymore, can somebody summarize the whole gist of this lesson? What's the gist of it? What's the idea? The overarching idea that we're doing or going through here? Nobody? Go ahead, Tori.
Alright, so what we're doing is we are finding the solutions on graph. We're finding how to graph these quadratics that we just learned how to factor, and we use the factorizing, the factoring methods that we learned to find the solutions and find the graph.
Okay, good. Now, what's one thing maybe to add to that? That was absolutely what we're doing. There could be 1 or 2 things to add. What's something to add to it? So Tori May already said we're using the factored form to come up with our solutions. We're graphing on number lines with quadratics.
Using inequality.
They're inequalities. Very good. That's something we didn't mention. These are inequalities. That's very important. Because inequalities are what give us solution sets or regions of solutions, right? Whenever it's an inequality is when we end up getting this shaded idea from inequality. So it's definitely an inequality. Okay, and then the last thing to remember is that we want to test points in all of these regions, but not the critical points. We don't test the critical points because those will give us 0 in the answer. Because that's what we solved for in the beginning. Okay, that's what we solved for in the beginning.
Oh, and it's good because then we can find out what is not in the equation.
Then we can find, then what is not in there. That's true. Okay, this is definitely not in the solution set. Now, had it been greater than or equal to 0, they'd be shaded in, and it would have been just all real numbers. Again, if this was greater than or equal to 0 in this example, you shade these spots in, and it would be all real numbers. All right, try this one on your own now. Please.
Zero.
25.
Stop.
I have to make it work. That's what I was checking. It works.
Yeah, he got us. He got us, guys. He got us, homies.
Yeah.
Fricka fresh.
Practice?
Talking.
Practice for a second on your own, please. Okay? Make sure you remember what you need to do whenever you solve these. Remember the first step, you need to move stuff, so make sure you move. Look for your GCF, then go into factoring. Make sure you go through your steps. After about 20 seconds at a time, I'll put up one step at a time. So if you want to keep checking back, I'll give you like 20 seconds between each line. Okay, first step is going up if you want to check. Second step is going up. That's barely visible. Can you see that in the back? Georgia, can you see it back there? Okay. It's very light. So make sure you take out that GCF before you start. And don't ignore the GCF because it's going to be one of your factors. Third step is up. Here's my critical points. Check your critical points, please. Make sure they're right. I'm going to move the first few steps off the page, so I'm just going to slide up a little bit. Once I have my critical points, I make my number line. These are all open circles. All open circles, simply because it was less than, not less than or equal to. We are looking for a negative region. We're looking for a negative region because of this less than 0. Any number less than 0 is negative, so we're looking for a negative region to shade. We have 4 regions to test. We should test them in the factored form. You got them for me? In order from left to right, tell me positives or negatives for the regions.
I did it from the other way.
Ah, okay, so tell me the reverse then.
My first one I got negative. No, that one.
Yeah, it's
No, like 5, like I started from the right to the left.
Okay, so start from the left to the right.
And I left out 0. So I forgot that 0 counted.
Ah, I got
So
you.
I got negative, negative, positive when I should have gotten negative.
Some alternating. Can you give me your 4? Natalie, go ahead.
Negative, positive, positive, negative.
Yeah, that's basically what I got.
You forgot the 0 there. Guys, it happened to work out okay for you, except for the fact that 0 is not in the solution. So that would change your answer, right? So we want to know when this is negative. When this is negative, it's negative here. Is this right, by the way?
It's negative, positive, negative, positive.
I'm trying to trust you guys. Let me do a quick mental check. That's definitely a negative, folks.
It's negative, positive, negative, positive.
Relax, relax. Okay, who said that, Liam? Yeah. Okay, please check. Your answers will be here. And here. You're welcome, guys.
Some drug. Sorry, excuse me.
oh my god,
You got it, Worth? And here's your homework for this section from the oral and written exercises in section 4.9.